Okay, welcome back everyone. In the second part, we're going to talk about energy and rotational motion. So what we're trying to get out of this segment is to talk about the moment of inertia and what this quantity has to do with the shape of a rigid body, and then talk about how to calculate rotational kinetic energy using the moment of inertia. Before we do that, we'll do a quick practice problem that goes back to last unit. And we are given the angular velocity of a flywheel described by this equation. And we want to determine the angular displacement from t equals 0 until the time when the flywheel reverses its direction. So we know that when it reverses, basically omega final will be 0. So we just set this up. So 0 is equal to 8 minus 2t squared. So this means that t is equal to basically plus or minus 2 seconds. And the one that's going to work for us is 2 seconds. Negative time won't really work for us. So since this is not linear, we can't just plug into here and do theta is omega times t. We actually have to break it down and integrate. Okay, so since omega is d theta dt, we can break that down and say d theta is omega dt, and then we just integrate that. Okay, so we're going to integrate d theta prime from 0 to theta, because that's what we want is the angular displacement. And then we're going to integrate from 0 to 2 of omega dt. Okay, so the left side is just theta, and the right side is going to be 4t squared minus 2/3 t cubed, evaluated from 0 to 2. And so that's going to be 4 times 4 minus 2/3 times 8. So that's 16 minus 16/3, which is going to give us 32/3. And that's going to be radians. Okay, so that's theta, or if you wish, delta theta. Okay, so on to kinetic energy. Okay, let's take a moment just to talk about inertia first. Okay, and in linear motion, inertia is the same thing as mass, but rotating systems have what we call rotational inertia. And for a system of particles, I is equal to the sum of mr squared. So technically, I is equal to the sum over I of mi ri squared. It's not the whole thing that's squared, it's just the r. So that's the definition of I. And if you have solid objects, it's a little bit more complicated. This number is for the 13th edition of the textbook, but there is a table in chapter 9 of your textbook. So let's just look at an example problem. And so we have a 2 and a 3 kilogram mass that are mounted on opposite sides of a 2 meter long rod of negligible mass. What is the rotational inertia about the center of the rod? Okay, so here's the 2 kilogram, and it's connected by a very light rod to a 3 kilogram mass. And basically, the mass of the rod is not playing a role right now. So what's the rotational inertia about the center of the rod and about each mass? So we'll have the center, we'll have the left, and we'll have the right, assuming that the axes of rotation are perpendicular to the rod. So we'll start with the left. Okay, remember that the moment of inertia is the sum over I of mi ri squared. So that's just going to be 2, and we're going to say that basically this location is where x is equal to 0. Okay, so the left mass would be a distance of 0 from the axis of rotation. The rod itself doesn't count, so we don't care. And then it would just be 3 times 2 squared. So that's just 12. and the correct units are kilograms, meters squared. Okay, so, whoops. So just 12 kilogram meters squared. Okay, in the center, well, now we would have 2 times -1, that gets squared, and then 3 times +1, and that gets squared. So that's only going to be 5. And then finally at right, now the 3 kilogram is at r equals 0. So we would have 2 kilograms times -2 squared plus 3 kilograms times 0 squared is just going to give us 8 kilogram meters squared. Okay? All right, so now that we've talked a little bit about moment of inertia, we can discuss kinetic energy. So again, objects that are moving in a straight line have translational kinetic energy, 1/2 mv squared. Bodies that are rotating have rotational kinetic energy. So m is kind of getting replaced with the moment of inertia, I, and v is getting replaced with the with the angular velocity omega. Okay? Now, there is a neat little transition that we can talk about when we have the center of mass, but we'll get to that a bit later on. And it is possible to have both forms at the same time. So you can have an object which is rotating, so it has omega, and the center of mass is moving, so it has translational. So it is possible to have both. Okay, so here's an example. We have a 3 meter long lightweight rod that has a 1 kilogram mass attached to one end. And then we're going to have 1.5 kilograms attached to the other. If the rod is spinning at 20 RPM, about its midpoint, about an axis that's perpendicular to the rod, what is the resulting rotational kinetic energy? So first we have to calculate the moment of inertia, and remember that's the sum of mi ri squared, and we're picking the center of this rod, so everything's 1.5 away. Okay, so it's going to be 1 times 1.5 squared plus 1.5 times 1.5 squared. Okay? And so if we calculate this all out, essentially we're going to get 2.5 times 1.5 squared. So it's going to be about 5.63 kilogram meters squared. Now omega is 20 RPM, but remember we multiply that by 2 pi radians over 60 seconds to convert that. And we can get the rotational kinetic energy, therefore, by doing 1/2 I omega squared. So it's 1/2 and then 5.63. I rounded that a little bit. And then this is going to be 2 pi over 60 times 20 radians per second, which will then be squared. And if we plug all that in, we'll get a final answer of, let's try this real quick. We're just plugging away real quick for this. And I got about 12.3 joules. Okay, so you can check and see if you got the same thing. All right, let's do one more example of this. Okay, and this is a solid ball of mass 300 grams in diameter 80 centimeters. It's thrown at 28 meters per second. So as it travels, it spins with an angular speed of 110 radians per second. What is the translational kinetic energy, the rotational, and then the total? So translational, so Ke translational is pretty easy. That's just 1/2 mv squared. So that's the speed that it's traveling with. Okay, so it's 1/2 0.3 kilograms and then 28 meters per second squared. Whoops, that went forward too fast. Okay, and that's about 118 joules. Wow, it's not liking me today. The rotational kinetic energy, so Ke rotational, is going to be 1/2 I omega squared. Now, the thing is, this is a solid ball, and the moment of inertia for a sphere is 2/5 mr squared, where m and r are the mass and the radius of the sphere. And this is a calculation that you can do, and we'll do a couple of examples of this in the next video. But for now, this is something that you could just look up because it's a sphere. Okay, so we plug that into this, 2/5 mr squared, and then we're given omega squared. Okay, so we plug all those numbers in, and what we get for that is 1/2 times 2/5 times 0.3 times 0.4 squared. So that's R is 0.4, okay? 80 centimeters divided by 2 is 40 centimeters, and then that's put into a radius. And then that's thrown at 28 meters per second, and that's squared. So that's meters, that's kilograms, and I'm being really bad with units. I hope you'll forgive me. Okay, so 28 squared times 0.4 squared times 0.3 times 0.4 times 0.5. I just did this backwards for some reason, but that comes out to 7.53 joules. And so that means that so that's Ke rotational. So that means that Ke total is the sum of Ke translational plus Ke rotational. Whoops. Can you tell what the next slide is going to be? So that's about 126 joules. Okay, now when you get problems like this, you're going to be given what type of object it is. Okay, so next time we are going to talk about how to calculate rotational inertia. So we'll see you then.